All right. In the last video, we made this pair of HR diagrams. In this video, we're going to model them and determine things about this cluster. What we're going to do is we're going to match, just using our eyes, we're going to match an isochrone curve to the data. So what is an isochrone? Well, iso means same, chrone means time. So these are curves all at the same time. Star clusters, as I've already described, the cloud collapses and the stars form all about the same time. But you end up with stars of different masses. And these stars end up in different places on the HR diagram. These purple curves are isochrones, and each point along the curve corresponds to a star at a different mass. But these are all at the same time. If I move this age slider, the isochrone curve will move, and it shows you where stars of different mass end up at a different time. Okay. So let me show you a figure. This is an HR diagram that shows the main sequence. The main sequence is when a star becomes a star. The little cloud has collapsed to the point that in its core, it's gotten hot enough that it can fuse hydrogen into helium. It's generating its own energy. That's when we consider the star as having turned on, and stars of different mass, when they turn on, end up in different places in the HR diagram on this main sequence. The massive stars, they burn luminous and hot. And so you see them up here. Here's a 15 solar mass star, 15 times the mass of our sun. It's much more luminous. This is 1 solar luminosity. So here we're looking at probably a few thousand solar luminosities. And it's hotter, it's bluer. Our sun is right here. This one is burning much hotter. Or here's a low mass star, just 1/5 the mass of our sun. And it's low luminosity and burning cooler. So it's red in color. Okay. So let's play with this age slider. The unit here is logarithmic. If you see 6, that actually means 10 to the 6. 10 to the 6 is a million years. If you see 9, that's 10 to the 9, a billion. Once you get up to like 10 to the 10.1, 10 to the 10.2, that's like the age of the universe. The universe is almost 14 billion years old. Okay, let's move it up and see what happens. And what you see is the upper end of the main sequence. The massive stars are leaving the main sequence first. Now, the massive stars, they have more fuel. You may think they'd stick around longer, but even though they have more fuel, they're burning it even faster. I like to say that massive stars live hard and die young. So it's beginning the process of dying. It's a multi-step process. But once you leave the main sequence, it's going to happen. So what's going on? Let's do some stellar physics. So when on the main sequence, stars are in what we call hydrostatic equilibrium, HSE. They're balanced. Gravity is trying to squeeze them smaller, but because fusion is going on at the core, which we colloquially call burning. It's not burning like chemical burning, but we use the term. So nuclear fusion means we're burning hydrogen and producing helium. And that produces energy and pressure that pushes back against gravity, and everything is in balance. And so as long as that fusion is going on, we can be in a balanced state for a very long time. Take our sun. It's been on the main sequence for 4.5 billion years and has another 5 billion years of stability. Now, stars are made out of primarily hydrogen and helium. They're the primary elements in the universe. Hydrogen is just a proton. very simple particle with an electron around it, but the nucleus is a proton. Okay, hydrogen is a proton. Helium is a combination. It's two protons and two neutrons together. And most of the helium in the universe was made between minutes 3 and 20 after the Big Bang. Back then, the universe was much smaller and much denser. Basically, every point in space was like the inside of a star, dense and hot. And so fusion was proceeding. Hydrogen was being turned into helium, but after 20 minutes after the Big Bang, the universe had expanded so much that the density and temperature dropped to the point that fusion stopped. So the universe was left with a lot of hydrogen and some helium. Everything else, for the most part, was made in the bellies of stars, is being made in the bellies of stars very slowly with time. Okay. Let's talk about this fusion process that's going on in stars. So don't be scared. It's a complicated diagram, but this is the process that is the primary fusion process in the sun. This is called the proton-proton chain. Basically, a proton runs into a proton and they stick together. In the process, one of them gets turned into a neutron. So we call that a deuteron. And then that deuteron runs into another proton, making helium-3, 2 protons and a neutron. Once you have 2 protons, you're now helium. As you change the number of protons, you change the element. And then finally, this helium will find another helium, making a helium-4 and spitting out 2 extra protons that get thrown back in the mix. Those 2 protons were just catalysts. So overall, you end up with 4 protons coming in and helium-4 coming out. This is the simplified version. And energy, when you stick those protons together and turn 2 of them into neutrons, those neutrons have less mass than protons, and through E equals mc squared, a little bit of mass is turned into energy. And that's what's fueling the sun. That's why the sun is so bright. It's what holds it up. That's the proton-proton chain. Now, in more massive stars, you have a different nuclear reaction. This is called the CNO cycle. Here, carbon acts as a catalyst. Here we see a carbon nucleus. It runs into a proton. Hydrogen 1 is a proton, making nitrogen. And it then decays into heavy carbon, runs into a proton, making heavier nitrogen, runs into a proton, making oxygen, which decays into even heavier nitrogen, runs into a proton, and then this spits out a helium nucleus and carbon. And so the carbon gets thrown back into the mix. It's a catalyst, but it facilitated the production of helium from 1, 2, 3, 4 hydrogen. So same kind of deal, 4 hydrogen go in, helium comes out, and energy. And again, this dominates in massive stars. So in the core of a star, as this process continues, hydrogen's converted into helium until eventually, and this is for our sun, after 10 billion years, in the very, very center, it's pure helium. You get out away from the center and you still have hydrogen fusing, and you get far enough out and it's just hydrogen sitting around, not hot enough to burn, to fuse. And this is when you leave the main sequence. This is when you're out of equilibrium. What happens is here we have that leftover helium, and it's not hot enough to burn. It's just, again, colloquial language, we call it ash, comparing it to chemical burning, but it's not. It's fusion. It's just what's left over. You have this growing pile of helium ash at the center of the star, and it's not producing energy. So it contracts, it shrinks. And this is a little counterintuitive, but when something shrinks, it releases energy, and a lot of energy. You have gravitational potential energy being converted through its collapse into kinetic energy and heat. Here's a good way to demonstrate it. This, I've got a marker. I'm holding it above the ground. It has gravitational potential energy. I drop it. So that was converted into kinetic energy. And when it hit my desk, that was converted into heat, warmed up my desk just a little bit. So this non-burning helium core is contracting, and gravitational potential energy is being converted to heat. That is heating the surrounding hydrogen burning shell. It's still fusing in that shell. And when you heat it, the reaction rate goes way up and it produces a lot of energy. And that energy boosts the outer layers, inflates them, makes them bigger. And as they spread out and become less dense, they get cooler. In other words, you make a red giant. And it's funny how stars work. The core is contracting, and that's making the outer layers expand because of this mirror effect produced by the hydrogen burning shell. Okay. So we're making a red giant, and that's what's going on here. You're seeing these most massive main sequence stars move over here to the red giant part of the HR diagram. Luminous red stars, red giants. Let's increase the age even more. I'll keep going here. And then you see this curve right here. That is called the horizontal branch. And you only see that in really old things. You'll see it in your globular cluster, maybe not so much in the open cluster. Okay, what's going on here? Let's go back to the images. So this helium ash keeps contracting and heating up and contracting and heating up. Eventually, it gets up to about 100 million Kelvin. And that's the ignition temperature of helium. And it goes through a process where two helium run into each other and stick together, and then another one sticks together, and you end up with carbon. And in the process, it releases energy. This is called the triple alpha reaction. A helium nucleus is called an alpha particle. So for a long time here, the core wasn't producing energy, but all of a sudden turns on again. So it's going to be the whole process in reverse. Now that core is producing energy. It's going to expand. It's going to take that surrounding hydrogen burning shell, spread it real thin, make it bigger and spread it thin, and the reaction rate goes down so it can no longer poof up the outer layers. And so the outer layers will shrink and heat up. Again, the outer layers do the opposite of the core because of the mirror effect of that hydrogen burning shell. Core is now expanding and heating up, and the outer layers are contracting and cooling down. So going back to the HR diagram, you can see that. So we're starting over here, helium ignition occurs, and you end up over here. As you move diagonally in this direction, you're getting smaller. And of course, as you move to the left, you're getting hotter. So we're going from large, cool stars to slightly smaller, but still pretty big, hotter stars on the surface. And this region we call the horizontal branch, simply because it's horizontal in the HR diagram. But these are helium burning stars. The main sequence, hydrogen burning stars. And they're stable until you run out of hydrogen. Here, these are helium burning stars, and they are also stable until you run out of helium. They're in hydrostatic equilibrium. We once again have restored balance between gravity and pressure. When something's in balance, it can be in balance for a long time. And when you get out of balance, you get change, and the change happens quickly until you're in balance again. Now, even so, they don't spend a lot of time on the horizontal branch. Take our sun. It spends about 10 billion years on the main sequence, but only about 100 million on the horizontal branch. So a much shorter period of time. before it uses up all of its helium at its core, in which case it will exit hydrostatic equilibrium and continue on closer to star death. Okay. Now, we have one more parameter to understand before we can start matching these isochrone models to the data, and that is metallicity. So what is a metal? An astronomer has a different definition than a chemist. Let me show you the astronomer's periodic table. It's very simple. We have hydrogen, we have helium, again, both made shortly after the Big Bang, and then we have everything else. And everything else we just call a metal. Okay. The way it's measured, metallicity 0 means the same as the sun. Metallicity 1 means 10 times that of the sun. -1 is 1/10. -2 is 1/100th. Now, old star clusters, like your globular cluster, very old, it will have a low metallicity. It was born at a time when the universe was primarily hydrogen and helium. But stars, it's a cycle. Here we have a cloud of gas, make stars. The stars die. They explode in different ways that we'll learn about as we go on through the course. And in the bellies of the stars, you're making heavier things, carbon, oxygen, nitrogen, and everything else. And when it explodes, it's scattered into space, gets incorporated into clouds, and into the next generation of stars. And they make more metals, explode, and it continues and continues. Kind of early generations of stars won't have planets because planets are made of what astronomers call metals, and they didn't have them then. You are made of what an astronomer calls metals. And to have enough metals to make you and to make the Earth, you have to go through this cycle about 50 times. You, or the parts that you're made of, your atoms, have gone through about 50 supernova explosions to make enough of the stuff to make you. So the globs, the globular clusters, will have low metallicities. But the open clusters, they're young. They're produced recently after many, many generations of star formation. They will have higher metallicities, closer to solar. And what this does, the metals, they change the opacity of the gas, how easily light and heat can escape. It affects the structure of the stars. So it changes where the isochrones are. For example, I'll increase the metallicity from -2 out to 0 or even higher, and you see how the isochrones changed. Or I'll go down to a young cluster and show you, there are changes there as well. So metallicity can't be ignored. It changes the location of the isochrones. Okay, now you know all the parameters. So we're going to fit this data. Well, we're going to match it using our eyes. Couple things to remember. The foremost primary thing to remember is to take your time. No need to rush through this. We have a large parameter space to explore. We want to get it right. Now, your distance is pretty close to right. You can tweak it if you want, but I would start with age. And I'd increase the age until you touch the stars here. So the turnoff point kind of matches the stars. Next, I'd adjust the metallicity. I'd try to get the curvature right. You see the curvature in the data, particularly on the red one. I find it easier to see the curvature. Kind of want to match the curvature. And again, keep, like that's too much. The data may not quite fit yet, but try to match the curvature. This goes whoop, and so my curve goes whoop. Okay. And keep in mind, globular clusters will have a metallicity on the low side. Open clusters will have a metallicity on the high side, and that will help you. The next, adjust the reddening. There's dust between us and these stars, And so you can guess how much dust and try to slide that over to your isochrone. And then just keep cycling through. It's like, okay, I'm going to decrease the age, work on the metallicity. I'll keep fine-tuning this in a second, but let me give you a couple hints. First of all, you may want to change your browser size. Most browsers come in this size here. Give it a second to reload. And all the points are getting squished together. You may want to hit Control minus a couple times or Command minus on a Mac and give yourself some more screen, give your HR diagrams some more screen real estate. And the dots also get smaller. Let's see, I'm going to have to reset my distance here. It forgot it after I changed the screen size. Another thing you can do is, right now we're in standard view, which is great for seeing how the isochrone moves as you change age and metallicity. But you can do frame on data. Now, you do have some data points, particularly down here at the bottom. These are the stars that were just barely detected. They have huge error bars, particularly in the horizontal direction. And so we want to decrease the maximum error bar to get rid of these, so you can frame it up a little bit better. You'll see what I mean. I'm getting rid of them. One more I want to get rid of. There we go. And once I got rid of those stars with a lot of scatter, it framed up nicely. So now I can really see what I'm doing, and I can try to do it even better. So I'm going to just play for a second here. Maybe I'm going to decrease the reddening. Try to get this curve to match better over here. Increase the metallicity. Now I'll play with the age, tucking that around. I want these curves to go through my red giants. These right here, these few points over here, if I go back to my image, you see the bright red stars here, 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 here. Those are the red giants. Those are these points right here. So I want to hit them. Now, two more considerations as you're doing this. Let's get into some subtleties, but they're important. Half of these are binaries. Half the systems out there are binaries. You had two stars orbiting each other. But we can't resolve that. In our picture, those two stars are right on top of each other. And so what we see is something that's brighter than it should be. So half of these stars, the reason you see all this vertical scatter, the high ones are actually binaries. We're getting more luminosity there than we would for a single star. So you kind of want to match the isochrone to the bottom. The isochrone is for single stars, binaries right above. Unless you're down here at the faint end. The faint end, you have a lot of scatter, a lot of error, and it's going to scatter it in both directions. So the faint measurements will straddle the curve. Some will be above, some will be below, just because of the uncertainty. But up here, where you have really good measurements, your curve should touch the bottom and the binary should ride above. I'll tweak it just a little bit more. Also, there are little arrows here if you want to do fine adjustments. Now, As I said before, you can tweak the distance, but don't tweak it too much. It's been pretty well defined by Gaia, but you could play with that a little bit. Anyway, I could keep playing and fine tune it a little bit more. It's never going to be perfect for a wide variety of reasons. These isochrones are created on a computer based upon a model of how stars work, and these models get better each and every year, but they're not perfected yet. Some of the calibration in these different filters may be off, or you may have just a really complicated cluster. Sometimes all the stars didn't form at the same time, or there may be some dust mixed in, so they're not all behind the same amount of dust, etc. And those, if you have one that simply can't fit, those are actually the interesting ones. Those are the ones astronomers would want to study more. Anyway, do your best, take your time, and then when you're done, you're going to record it in a spreadsheet. The spreadsheet's linked in the lab. So here's your young open cluster, your intermediate age open cluster, and your old globular cluster. And you're measuring distance, log of the age, metallicity, and the reddening. And here it's for different teammates. Each teammate should measure every cluster and put your best measurement there, and we'll have a group average and group standard deviation. And you're welcome to work together and help each other. That's okay. But this will give you an idea of how accurate these measurements can be done. And in a future video, we're going to supplement our data with archival data. We're going to load in some Gaia data, some 2MASS data, extend our data set down to fainter measurements, see more of the main sequence, also different frequencies. We'll go out of the visual band into the infrared, and this will help us constrain the model even better. But we're going to start with just your Skynet data. The last thing I want to point out is the globs. I've already said this, they're really far away. And so you're not going to have a lot of the fainter stars, and you might not have anything. Set this up to look like a glob. So here's a glob. You may not have any data down at the turnoff point. And so for the globs, you'll have to try to use the horizontal branch to set the date. They're going to be the hardest ones, being far away. You don't have enough stars. That once we add in the archival stars, that will help them out a lot. Okay, that's it for this video.